Our experiments with battery and capacitor indicate that charges can move inside conductors. Initially, the capacitor was discharged. We connected it to the battery and moved the negative charge from the lower plate to the upper plate. We then discharged the capacitor by connecting it through the light bulb. So we see that the flow of charge can produce various effects that can be observed. We made a light bulb glow. The light bulb was heated up. The energy stored in the capacitor was converted into the heat energy of a light bulb. Of course, there can be other effects produced by electric current. For example, we can turn an electric motor. Very often, we are interested to know how much charge passes through the conductor or other electric device during the given period of time. For this, we calculate a quantity called electric current I, which is the rate of flow of charge through the conductor. If charge delta Q passes through the electric device during time delta t, then I is defined as delta Q divided by delta t. In the SI system of units, the current is measured in amperes. The current of 1 ampere carries 1 coulomb of charge per 1 second. Here is another way to define the electric current. Imagine we have a conductor and charges move through the area of the conductor, say the cross-section of the wire, in the perpendicular direction to the area of the wire. If delta Q is the amount of charge that passes through the area A in time delta t, then we can define the average current during this time delta t, given by delta Q over delta t. If the rate of charge varies with time, we can define the instantaneous current, I of t. It is given by the average current during each infinitesimally small time interval dt. So I of t is equal to the limit of delta Q over delta t when delta t tends to 0. An important property of charge flow is conservation of charge. This means that the total charge in the conductor is conserved. The amount of positively charged particles in the conductor remains the same. This means that if charge increases in one part of the conductor because of the motion of charged particles, it must be accompanied by a compensating decrease of the charge in the other part of the conductor, so that the total sum of the changes remains 0. Now, if we pause for a second and think about it, the whole idea of small charged particles moving inside the matter may appear too preposterous or too abstract. In the end, we don't see the charges with our naked eye. How do we know they are there? My answer to this is that by observing various electric effects, such as charging and discharging the capacitor, we know very confidently that charges move and carry energy with them. Since the 19th century, scientists and engineers developed a beautiful and detailed theory of electric currents. This mathematical theory successfully describes electric currents across many disciplines. Even more, if we put equations aside, we can visualize motion of electric currents with a simple physical picture. The picture is based on a close analogy between the motion of charges in the electric field and motion of massive objects under the force of gravity. We have discussed several times that the equations describing the electric Coulomb force are very similar to equations describing the Newton's force of gravity. Similarly, equations describing electric currents are very similar to equations describing the motion of water current in hydraulic systems. If you learn how to apply this analogy, you can predict many properties of electric circuits without doing lengthy calculations. To visualize what happens inside an electric circuit, it might help sometimes to think that it is analogous to a water slide in an amusement park. Flow of electric charge, or electric current, has many similarities to the flow of water in the pipes. Components of an electric circuit are analogous to the hydraulic devices that are included in the slide. The electric potential V corresponds to height in potential space. Of course, this height is purely imaginary, but equations describing it are very similar to equations for gravitational potential. Some parts of the circuit will have higher potential or larger height, Some of them will have lower potential. Water will generally flow from higher potential to lower potential. Similarly, the electric current. Various parts of the circuit are similar to common devices inside the water slide. Each switch plays the role of a valve, battery of a pump that pushes water from the low potential to high potential. The pool behaves like a low resistance conductor. Water propagates through it very easily. On the other hand, devices like filters that slow flow of water play the role of the high resistance conductor. So therefore, a typical circuit will include elements to move charge around the circuit. These are called sources of electromotive force, batteries, solar panel alternators, and so on. There will be devices to store charge, capacitors, devices to conduct charge, wires, vacuum tubes, etc., devices to extract energy from moving charge, such as light bulbs and motors, and finally, devices controlling or modifying motion of the charge, such as switches, transistors, transformers, and so on. We will use special common notations for the various circuit symbols shown on the right-hand side. You can see common symbols for the capacitor, battery, and switch, resistor, and the light bulb. Let us now briefly review what happens inside the material when the current flows through it. We will pretend we take a powerful microscope and zoom on the moving charges to see how they propagate between the atoms of the material. We already classified materials according to their propensity to let the charge go through. One class of materials, called dielectrics or insulators, are resisting the motion of charge. It is hard to transport charge through dielectrics by a long distance. The other class of materials, called conductors, allow the charge to penetrate very easily. Metals are a very good example of a conductor that is used in many applications. Finally, fluids can be either conductors or insulators, depending on how many charged particles are present in the fluid. Suppose we first focus on dielectrics. In dielectrics, almost all protons and electrons are bound in tightly connected molecules. It is very hard to separate protons from electrons, so therefore there is little free charge that can be used to create the current. So therefore, when an electric field is applied to dielectric, the main effect of the electric field is to polarize molecules, to separate the charges by a small distance without breaking bonds in the molecules. The molecule as a whole has no electric charge. Therefore, it only gets polarized by the field but doesn't move an appreciable distance. In contrast, in metallic conductors, electrons can move long distances between a lattice of positive ions, which are metal atoms with a few stripped electrons. Moving charge in conductors is mostly negative. Only electrons move substantial differences inside conductors. The charge motion, however, is not entirely free. As electrons move between the atoms of the lattice, they frequently scatter on atoms and lose most of their velocity. Here is what happens inside a typical wire. Suppose first we have no electric field inside the wire, so our battery is off. In this case, individual electrons move very randomly in all directions inside the wire because of the heat motion. They have a very large thermal velocity of about 1 million meters per second. However, the whole electron cloud is at rest because motions of each individual electron is uncorrelated with the rest of the cloud. If we now connect a battery to this piece of the wire, the battery will create an electromotive force. Suppose this force points to the left. If moving charges were positive, they will also be moved to the left. However, in the metal, most of the free charges are electrons, which are negative. This electron cloud will be pushed to the left against the electromotive force. However, as the electron cloud displaces to the left, it will be increasingly attracted to the stationary positive charges. What happens next depends on whether the circuit is open or closed. the circuit is open if its two ends are not connected to one another. For example, we will get an open circuit by connecting a battery to two plates of the capacitor. For the open circuit, the returning force on the electron cloud from the positive charge eventually cancels the electromotive force of the battery. After a while, these forces cancel each other. The whole cloud stops moving. There will be no persistent current in the circuit. On the other hand, if the circuit is closed, it forms a loop along which the electrons can flow in a continuous motion. The solution of equations for electric forces in this case prefer a constant electron current, in which case the electron cloud drifts clockwise with small velocity of order 10 to the negative 5 meters per second. Individual electrons are pushed along each part of the circuit by small induced surface charges at the bends of the wire. In each part of the circuit, the electric field goes approximately along the wire. So therefore, to change the direction of motion, the electrons must experience the force created by additional charges. These charges are the negative and positive surface charges that accumulate at the bends of the wire. If the external EMF is constant, and we wait long enough for the current to establish, after a while the current becomes steady. In this case, the amount of charge passing through any cross-section of the conductor per 1 second is the same. So therefore, if we take two cross-sections, A and B, the charge passing through A per 1 second will be exactly the same as the charge passing through B in 1 second. If we calculate the average currents, dq over dt, at points A and B, they must be exactly the same. This reflects an important fact of conservation of charge. If we take a continuous piece of the conductor and measure the currents at 2 points in the conductor, the current must be the same at both points. In summary, in the presence of an electric field, in spite of all the collisions with atoms, the charge carriers slowly move along the conductor with a drift velocity, called Vd. The electric field exerts forces on the conduction electrons in the wire. These forces cause the electrons to move in the wire and create a current. Here is a cartoon of motion of charge carriers through the metal. The zigzag black lines represent the motion of a charge carrier in the conductor. Each charge carrier will be scattered numerous times with the atoms in the lattice. However, the whole cloud drifts in the rightward direction with the net drift velocity Vd. So the sharp changes in the direction of each charge carrier are due to collisions, and the net motion of electrons is opposite to the direction of the electric field. However, a very important convention is to assume that the direction of the current is equal to the direction of the positively charged carriers. So therefore, in metals, the direction of the current by convention is assumed to be against the direction of the motion of negative charge carriers. Even when the macroscopic current is large, the actual drift velocity of charge carriers is very small. Let's assume a copper wire with one free electron per atom contributed to the current. The drift velocity in this copper wire carrying a current of 10 amps is of order 2 times 10 to the negative 4 meters per second. This is a typical order of magnitude for drift velocities. We can relate the magnitude of the current to the drift velocity of charge carriers and concentration of charge carriers inside the conductor. Let's look at the picture on the right. Suppose we wish to find the current through area A of the cross-section of the conductor. In this case, all charges that are within the distance delta x, which is equal to Vd times delta t, will pass through the area A during the time delta t. So therefore, the total number of charge carriers passing through the area delta A is equal to n times A times delta x, where n is the number of charge carriers per unit volume. The total charge delta Q that passes through area A per time delta t is equal to the number of charge carriers multiplied by the charge of each carrier, Q. So therefore, delta Q is equal to N times A times delta X times Q. Here again, the Vd is the drift speed, which is the speed at which the charge carriers move. Vd is equal to delta X over delta T, and hence delta X is equal to Vd times delta T. Finally, dividing delta T out, we will get the average value of the current. It is equal to N times Q times Vd times A.